All right, guys, this is 2-1 Patterns in Inductive Reasoning. So I'm going to go through this lesson here with you. Um, we're basically, if we're going to maybe give a definition of what is inductive reasoning, inductive reasoning is really just looking at patterns and finding the next number, shape, whatever that comes in the pattern. So we're going to be later talking about deductive reasoning, which is in one word defined to be proof. So we are looking at these patterns here. Um, so let's look at example 1a. We have one square, and then we have three squares, and then we have one, two, three, four, five, six squares. So there's a number pattern here as well as a shape pattern. I expect, let's see, I went from 1 to 3, it just kind of added these two here onto that shape. And then I went from 3 to 6, and it just added these three guys here. I'll fill in the squares. So I just expect to add another row in here. So our picture looks like this. You may have already drawn it, but what they're asking you to do is draw the next shape in the pattern. So there it is. It's adding kind of another diagonal row there to that pattern. It has actually in it 10 individual squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, here's a number pattern. We go from 1 to 2, 2 to 4, 4 to 7, 7 to 11. What I'm noticing here, this is something you'll have to watch for, is I go up by 1 here, then I go up by 2 from here to here, then by 3 from here to here, then by 4 from here to here. So I expect to go up by 5 and land at 16. So one of the things you'll be looking for if you're looking at the patterns in this assignment is what is it adding or subtracting? What am I adding or subtracting to get from one number to the next? You could also be looking for what am I multiplying or dividing when you get to that in part D. So next one, we have shapes here. We've got a triangle, and then a square, and then a regular pentagon is what that's called. So we have a three-sided, four-sided, then five-sided figure. So I expect the next one to be what's called a hexagon or a six-sided figure. So the way I draw the hexagon is get the top part first. So 1, 2, 3, and then the bottom three. 1, 2, 3. D, we have a number pattern. Like I said, when you get number patterns, you're going to be looking for common number that's added or subtracted, or multiplied or divided. In this case, going from here to here, we're multiplying by 3, so it's times 3. And then from here to here, it's times 3 again. To here, times 3 again. So 54 times 3 gives us the next number in the pattern, 162. There's some patterns in that section. There might be some where you'll just see letters, a string of letters. They could be representing the first letter of certain numbers. I remember one of them, one year we assigned, it was like J, and then F, and then M, and that represented January, February, March, things like that. Or I think we had an O, and then a T, and then a T, and that represented 1, 2, 3. They're like the first letters of the numbers. So some of those might be a little hard to see. It's not a big deal if you don't see the pattern. What you need to understand is that inductive reasoning means looking at patterns, and so um, you should hopefully be able to see it. Here's some techniques: shapes, adding, subtracting, multiplying, dividing. Those are the things to look out for. Okay, counterexample. Here is a counterexample. Unfortunately, I'm going to use the word in it, but it's an example. So really, we're just defining counter here, but an example that proves a conjecture false. And so a conjecture is just a hypothesis. It's a statement that you make that you think maybe is always true. But if you come up with a counterexample and it only takes one, then that conjecture cannot be proven to be always true. So here we're going to come up with some counterexamples here. It says for all real numbers x, the expression x squared is greater than or equal to x. So for all real numbers x, so if I start trying values like, well, like 2 squared is 4, so x squared in that case is bigger than x. If I go x is 2, and x squared is 4, and yeah, it works there. And if I keep getting bigger, 3, 4, 5, that works. What if I use x equals 0? That's a good one to try. X squared equals 0. Okay. I still fall into the category of or equal to. What if I try negative? What if I say x equals negative 2, and x squared would equal positive 4? Positive 4 is still greater than what I started with, so none of those work. I'd always encourage you to try a positive, a 0, and a negative, so negative, 0, positive. There's something else we ought to be thinking about, and we've got a hint here for us. Oh, it says think about fractions. So let's think about fractions. What if, do this in blue because this is going to work, x equals 1/2. Then x squared would be 1/2 squared, which means 1/2 times 1/2, and guess what that equals? 1/4. If you take half of a half, in other words, take half of 50 cents, you have less money than you started. So square a fraction, it gets smaller rather than bigger. So the counterexample is x equals 1/2. Okay. Here's another statement. It says for all real numbers x, the expression square root of x is greater than 0. So for any real number, square root of x is greater than 0. Oh, okay. Yeah, that works if I use like square root of 4 is 2. So for positive numbers, seems like it'll work. What if I ask for square root of, say, something like 0? Square root of 0 is 0, which is not greater than 0. It actually equals 0. So if, here's my counterexample, if x equals 0, square root of 0 equals 0, which is not greater than 0. So there it is. Right, and the last one here says if the product of two numbers is even, then the two numbers must be even. So if the product of two numbers is even, then the two numbers must be even. Is that true or false? Can you think of a counterexample? And let's just start thinking about it here. What if we have an even number? So we could have, so even numbers would be like 2 or 4, 6, 8, 10. Start thinking about factors of those. Well, here's 2, and I get 2 if only factors of it are 2 times 1. Right off the bat, that's a counterexample. We got 2 times 2 here, 2 times 3 here. This is 2 times 4 here. That works, but what about 1 times 8, right? So here's the deal. It says that if the product of two numbers is even, then the two numbers must be even. That's false if we have a product of, and you could pick several of these here. We could take just this first one of 2 the factors are 2 times 1, and 1 is odd or not even. I want to just say not even. So that's what we're looking for a counterexample. You'll be asked to do that. You're looking at patterns, looking for counterexamples, things like that. That's about it. Thanks for listening.